This is part 18 of a series of videos about multivariable calculus. We're focusing in on part 3 of a sub-series about the relationship between parametric curves and polar coordinates, though I'm mostly going to focus on polar coordinates in this video. We'll try to relate it to parametric curves at the very end. We're going to use Mathematica, this computer program, and in particular a command called polar plot to make a polar graph on a polar grid. I'm going to do things a little differently than I usually do. I'm going to start with an introductory question and answer that, and then move on to a related question before we get to our main example and then down to the exercise. So let's look at this introductory question. Suppose you've got a function f defined by a certain equation, y equals f of x, and let's assume that the domain of f, just to keep it simple, is equal to the set of all real numbers. This funny looking r represents the set of all real numbers. So those are the inputs. We'll also assume we've got real number outputs, just like you always assume practically all the time in pre-calculus and calculus. Here's the question. Just what exactly do we typically mean when we talk about the graph of f? Could you describe what we mean to somebody that you meet off the street or somebody in your math class? Think about it for a bit. Pause the video. How am I going to describe the graph of f? Well, you could certainly describe it as a set. You could think of it purely with set builder notation without thinking about any pictures. You could think of it as the set of all ordered pairs, x comma y, where x and y are real numbers. This is set builder notation, satisfying the property that, I'm going to put a colon here to say that that means satisfying a certain property. Sometimes people put a vertical line there. The second coordinate y must equal the output of the function f when you plug in the first coordinate x. So I'll say that again. This is the set of all ordered pairs, x comma y, such that, or satisfying the property that the second coordinate y is the output of the function when you plug in the first coordinate x. For example, for this function here, f of x equals 2x, when x is 3, y is 6, therefore the point 3 comma 6 is on the graph. But it's more than just a set. It's also visualized via a rectangular coordinate system, or more simply via a rectangular grid in the plane. Alright, I want to explain what that means here. First of all, we've got the graph of f here shown. F of x equals 2x. It's a straight line with a slope of 2. I happen to graph it for positive values of x. I certainly could have picked negative values as well. I'm purposely starting with positive values of x for another reason. So you see that, for example, the point 3 comma 6 seems to be on the graph. I can make that a little bit more clear by adding another option in here called grid lines, capital G, capital L. Arrow. If I put automatic here, Mathematica will pick where it wants the grid lines. There they are, and here we can more easily see that the point whose coordinates are 3 comma 6 in rectangular coordinates is on the graph right there. Alright, I also want to emphasize that you can change the grid lines, and this is going to be useful for us when we do the polar plot. And in fact, it's convenient to use the table command to create a list of values where you want the grid lines for x and y. Let me just type it and then I'll explain what it means. I have shown you this before if you watch these videos. This particular code here, if I separate it out from inside the plot, if I put it up here and enter it, we get a list of numbers 0, 0.5, 1, 1.5, etc. up through 5. We're getting the values of 0.5 times I, where I starts at 0, then it becomes 1, 2, increments up by 1 until you get to 10. This is where I want my x values for the grid lines, the vertical ones. They're going to be at every half unit instead of every unit. We can do the same for y. I can copy and paste this table command in here after the comma. I do need to change the 10 to a 20 to make sure I get up to a value of 10 when I is 20. Change that to a 20. There we go. And here is a finer grid showing us more detail about the graph of f. All right, and that would be a rectangular grid. Let's go down here to a related question. Suppose r equals f of theta is an equation defining a function f that still has a domain equal to the entire set of real numbers, r, and also has outputs that are real numbers. Just what exactly do we mean when we talk about the polar graph of f? Is it something different? Well, if you're thinking of it purely in terms of a set, the difference is pretty much just cosmetic. We could think of it as all the points r comma theta, where r and theta are real numbers, And we do switch around the role of the first and second coordinates here as far as which one is the independent and dependent variables. We usually think of the first coordinate here, r, as a function of the second coordinate. That is the most convenient way to do it typically. So you could think of it as this set. And if you think of it as a set, it's not that much different than the previous one. It's very similar. However, what's different is we visualize it on a polar grid, or a polar coordinate system in the plane. Mathematicus command polar plot can help us do that. Okay, I'm going to go ahead and enter this code, and we'll see a graph. It's still the same function, really, the doubling function, take an input and double it to get the output, but we're doing a polar plot. What's going to happen here? Will we get a straight line? The answer is no. We get a curve, in fact. How'd that happen? Well, here's the key. You are visualizing these points as polar coordinates of points in the plane when you've got this polar grid. So every point on this graph, this red graph that you see here, has an r coordinate, a distance to the origin that equals f of the theta coordinate, which is the angle that the ray from the origin through the point makes with the positive x-axis. For example, when theta is pi over 2, which is 90 degrees, what is r? Plug in theta equals pi over 2 into here, you'll get pi. So r, the distance to the origin, is pi, and you can see this point is a little bit further than 3 units away from the origin. Okay, that's the basic idea that you want to get down here and think about. I'd encourage you to pause the video and think about this before we go on to the main example. Alright, are you back? Now we go on to the main example. This one's much harder, and you're going to want to take lots of time to actually do a lot of calculations here to help you plot this, and it would be good if you had polar graph paper. You can find that pretty easily on the internet, and you could print it and use it to help you make the graph of this. You're going to need to find values of this function, for example, at pi over 6 radians. The value is 3 halves, 1.5. At pi over 4, let's see, did I enter this function? Yes, I did. Pi over 4, it looks like it's 1. At pi over 3, it's 3 halves. What about pi over 12, perhaps? Something like that. What we get? Let's try pi over 24. Here we get something more interesting. 2 plus square root of 3 over 2. You probably want to approximate those things. To help you plot it, think about the polar grid. Figure out how to plot it based on that. Pause the video. And here I'm going to come back and use Mathematica to look at that graph. Here's the basic graph with polar plot without a polar grid. I'm going to add the polar grid lines on here like I had before. Notice the use of table. I didn't mention that before. Notice how I'm using table. I'm looking at multiples of pi over 24 for the angle. Pi over 24 is going to be an angle of 7.5 degrees. I can copy and paste that down here. Let's put it in here, say. Need an extra curvy brace there. There's our polar grid showing us the graph of this. It's kind of a nice graph, like a 4-leaf clover. Here's your exercise. It's very similar. A little easier because you could plot fewer points and get an accurate graph. You might want to make a table of values. So you can use table to make a table of values here like I'm doing. These are all the points you would plot. The first coordinate being r, the second coordinate being theta. I did take the time to multiply the thetas by 180 over pi here so that these theta values are in degrees. So 15, 30, 45, 60 degrees. And here's the plot that you should get. A 3-leaf clover. A 3-leaf clover or flower or whatever you want to call it. I want to end the video by focusing on the fact that you can think of these in terms of parametric curves. I do want to look at the relationship between the parametric curves and polar coordinates, and in particular we can animate this. Why don't we go ahead and animate this one up here. I'll copy and paste this down here. I'll put it in the polar plot inside of manipulate. I'll make the right endpoint of the interval that I'm plotting this over be a b, which will be my animation parameter, as I've done many times. Start b barely bigger than 0 and go up to 2 pi. And let's see what we get. I think it does something funny with the polar grid lines at first. It doesn't make them completely over the entire range here. But as we watch the animation, I think they extend further. Well, maybe, yep, here they go, they do. There's our polar plot as an animation. It's getting traced out. You could think of this as a parametric curve. And you could think of it as a parametric curve in two ways. One way is you could think of it as a parametric curve in theta, in the parameter theta, where, let's see, where am I looking here, where you plot the polar coordinate, the points whose polar coordinates are r and theta, and where r equals f of theta, but you would need to interpret those points with a polar grid. It turns out you also can think of this in terms of rectangular coordinates, and I think I might do that in the next video. It's a little trickier, but that might be a nice way to see the relationship again between polar coordinates and rectangular coordinates. And I'll end the video there.